In this episode, we're going to take the mystery out of hyperparameter tuning by treating it like a disciplined experiment rather than a frantic hunt for better numbers. Hyperparameters are the settings you choose before training, like how strong regularization should be, how deep a tree is allowed to grow, or how quickly an optimizer updates a model. They are different from learned parameters because the model does not discover them on its own. You decide them, and training happens inside the boundaries they create. That decision shapes what the model can represent and how it behaves when it tries to learn, which is why tuning can feel powerful and also dangerous. Beginners often jump into tuning too early or tune too widely without a plan, then end up with results that are hard to trust and even harder to reproduce. The goal here is to show how grid search and random search fit into a broader idea of efficient tuning, and how guardrails keep you honest when you are tempted to chase a score. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful starting point is to think of hyperparameters as the knobs that control a model's personality, because they determine how cautious or aggressive learning will be. If you turn one knob too far, the model might become overly flexible and memorize, and if you turn another knob too far, the model might become too rigid and underfit. Some hyperparameters change the shape of what the model can represent, like depth limits or number of components, and others change how training proceeds, like step size or early stopping patience. The key point is that hyperparameters define the search space for learning, and they often interact, meaning the best value for one depends on the value of another. Beginners sometimes tune one knob at a time as if each knob lives alone, but real tuning is about combinations. When you keep this mental model in mind, tuning stops being random button pressing and becomes the process of exploring a space of behaviors to find one that generalizes reliably. It also helps to recognize why tuning is necessary at all, because that reason keeps you from treating it as a magical performance booster. Many models have default settings that are reasonable across many problems, but no default can match every dataset size, noise level, class balance, and feature structure. A dataset with many sparse categorical encodings behaves differently than a dataset with a few smooth numeric features, and a dataset with noisy labels behaves differently than one with consistent labels. Hyperparameters control how much the model trusts the data, how quickly it adapts, and how complex its internal rules can become. If you do not tune at all, you may end up with a model that is technically correct but poorly matched to the difficulty of the learning problem. If you tune without discipline, you can end up with a model that appears strong only because it got lucky on your evaluation split. Efficient tuning is about making the minimum number of experiments needed to find a stable setting that actually holds up. Grid search is the most straightforward tuning approach, and it is often the first one beginners learn because it is easy to describe. You choose a set of candidate values for each hyperparameter, then train and evaluate a model for every combination of those values. The advantage is that it is systematic, and it ensures you do not miss a combination inside the grid. The downside is that it can become expensive very quickly because the number of combinations multiplies as you add hyperparameters or add more candidate values. Even a modest grid with 5 values for 3 hyperparameters already creates 125 experiments, and that count grows faster than most beginners expect. Another subtle downside is that grid search spends equal effort everywhere, even in regions that are clearly bad, and it can waste time evaluating combinations that are not meaningfully different. That is why grid search is best used when you have only a few important hyperparameters and you already have a reasonable idea of the range that matters. Used thoughtfully, it provides a clear baseline for tuning behavior and can teach you which knobs actually move performance. Random search is often more efficient in practice, and the reason is not that randomness is magical, but that high-dimensional grids are mostly empty effort. In many models, only a small subset of hyperparameters has a large effect on performance, while others have smaller effects or matter only in narrow ranges. Grid search forces you to try every combination, which means you waste experiments varying unimportant knobs while barely exploring the important ones. Random search instead samples combinations from ranges, and it tends to cover the space more broadly with fewer experiments. It also has a practical advantage when some hyperparameters matter on a logarithmic scale, where values like 0.001, 0.01, and zero point 0.1 are more meaningfully spaced than 0.02, 0.04, and 0.06. By sampling from a range, you are more likely to discover the right order of magnitude quickly. Beginners sometimes distrust randomness because it feels less controlled, but random search can be more controlled than it appears if you set ranges intentionally and keep a fixed random seed for reproducibility. The deeper lesson is that efficiency comes from exploring the space in a way that matches how performance varies, not from exhaustively enumerating combinations. Choosing ranges is one of the most important tuning skills because a good search method cannot rescue a bad search space. A beginner-friendly approach is to start with plausible ranges based on how each hyperparameter functions, rather than choosing values that are arbitrary. If a hyperparameter controls strength of regularization, you typically care about whether it is very small, moderate, or large, and those differences often span orders of magnitude. If a hyperparameter controls model capacity, like depth or number of units, you often care about small, medium, and large capacity regimes, not about tiny step changes between neighboring values. Ranges should also respect constraints in your problem, such as training time limits, memory limits, and the need for interpretability. A range that includes overly large models might produce one impressive score, but create a system that is too slow or too fragile to deploy. Efficient tuning is not just about finding the best number. It is about finding the best number inside the set of behaviors you can actually live with. A critical part of efficient tuning is deciding what you are optimizing against, because the metric and the split strategy define what success means. If your evaluation setup leaks, tuning will amplify that leakage, because the search will reward settings that exploit the leak most effectively. If your evaluation ignores time order in a time-dependent problem, tuning will favor settings that fit mixed time patterns that will not be available in deployment. This is why validation discipline is not optional during tuning. It is the foundation that makes the tuning outcome trustworthy. Cross-validation can be used during tuning to reduce luck, but it must be implemented with leakage-proof pipelines so pre-processing happens inside each fold. In time-aware settings, you may need time-based splits or rolling evaluation so you are tuning for future performance rather than shuffled performance. Efficient tuning is not only computational efficiency, it is measurement efficiency, meaning each experiment teaches you something real about how the model will behave later. Guardrails are the rules you set to keep tuning from becoming a game where you win by overfitting the validation set, and they matter more than most beginners realize. One guardrail is a strict separation of data used for choosing hyperparameters from data used for reporting final performance, so you do not accidentally report a tune to the test result. Another guardrail is limiting the number of tuning rounds you run, because each round is a chance to adapt your choices to quirks of your validation data. A third guardrail is monitoring not only a single score, but also the stability of performance across folds, time windows, or segments, because a setting that wins by a tiny margin on average might be unstable and risky. You can also set guardrails around model complexity, such as maximum depth or minimum regularization, to prevent the search from drifting into highly overfit configurations. The point is that tuning should produce a model that is reliably better, not a model that is occasionally spectacular. Guardrails are what ensure your search rewards generalization, not clever memorization. It is also worth understanding that hyperparameters rarely act independently, which is why efficient tuning often focuses on a small set of high-impact knobs first. If you change model capacity, the best regularization strength often changes with it, because a more flexible model usually needs stronger constraints. If you change how features are encoded or scaled, the best optimization settings can shift because the loss landscape changes. This interaction is one reason beginners can feel lost when they tune, because one change seems to invalidate earlier results. A calm way to handle this is to tune in stages, where you first establish a sensible baseline model and pre-processing pipeline. Then tune the most influential hyperparameters, and only then consider secondary ones. Stage-based thinking is not a rigid recipe, but it prevents you from turning every experiment into a brand new world. Efficiency is gained when you reduce the number of moving parts at once and let each experiment isolate a meaningful cause. Another aspect of efficient tuning is recognizing when you should stop searching, because there is always another experiment you could run. If performance improvements become smaller than the natural variation you see across folds or time windows, you may be chasing noise rather than signal. If your best model is only marginally better than a simpler one, but is significantly more complex or less interpretable, the marginal gain may not be worth the operational cost. If different hyperparameter settings produce similar performance, but very different behavior on important segments, you should prioritize the setting that behaves more safely and predictably, even if it is not the absolute winner on the average metric. Beginners often feel pressure to maximize a score, but real systems are judged by reliability and maintainability, not just by a benchmark number. Stopping is a skill because it requires confidence in your measurement and clarity about your constraints. Efficient tuning means you stop when you have learned enough to choose a setting that is robust, not when you have exhausted every possible combination. There is also a practical danger in tuning called the multiple comparisons effect, which is the idea that if you try enough configurations, one of them will look best by luck alone. This is not about bad intentions. It is just how randomness works when you run many experiments. The more combinations you test, the more likely you are to find a model that appears to outperform others, even if the true expected performance is the same. That is why you need guardrails like a final untouched test set, and why you should look for improvements that are consistent across folds and time windows rather than spikes in one evaluation. It is also why logging your experiments matters, because it keeps you honest about how many tries you took to get a result. When you understand this effect, you stop treating the top score as a trophy and start treating it as a hypothesis that needs confirmation. Hyperparameter tuning is powerful, but it can also manufacture confidence if you do not control for repeated chance. Efficiency also comes from respecting compute and time constraints, because a tuning strategy that is theoretically thorough but practically impossible will encourage rushed decisions and sloppy evaluation. If a full grid search requires hundreds of long training runs, you might start cutting corners on validation or reusing results in ways that introduce leakage. A more responsible approach is to start with cheap experiments that narrow the space, such as a small random search with a limited budget, then refine around the most promising region. This approach aligns with how learning usually happens. You first identify the right scale and rough settings. Then you fine-tune if the improvements are meaningful and stable. Compute-aware tuning is not just about saving time. It is about preserving discipline by keeping the process manageable. When you keep tuning within a budget, you are more likely to keep your evaluation clean and your conclusions trustworthy. In real workflows, the most dangerous tuning is not the tuning that is slow, but the tuning that becomes so expensive that you start cheating to finish it. A beginner-friendly guardrail that often gets overlooked is to tune for behavior, not just for the headline metric, because behavior is what users experience. Two settings might achieve similar overall scores, but one might produce many false positives on a specific segment, or one might be poorly calibrated and generate misleading confidence. In a workflow where predictions trigger tree-off, those differences can matter more than a small metric gap. This is why segment checks and threshold behavior should be part of tuning evaluation, especially for imbalanced problems. It is also why you should monitor training stability, because some settings can produce unstable learning dynamics that are sensitive to small changes in data. A model that is slightly better on average but frequently unstable can be risky to maintain. Efficiency is improved when you define success in a way that includes stability and operational fit, because you avoid spending time polishing a model that will be rejected later for practical reasons. It is also helpful to connect tuning to interpretability and governance, because many real deployments require you to explain how the model behaves and why. A highly tuned model can become a fragile system of just right settings that is hard to reproduce and hard to justify. If you cannot explain why a particular setting was chosen, you risk turning tuning into an opaque ritual rather than an accountable process. This does not mean you need to explain every detail mathematically, but you should be able to say what each tuned hyperparameter controls and what trade-off you accepted, such as choosing a slightly simpler model to reduce overfitting risk. In environments where decisions affect access, security posture, or user experience, Governance expectations often push you toward models that are stable and understandable. Guardrails can include interpretability constraints, such as limiting complexity or requiring consistent performance across key groups. When tuning respects these constraints, the final model is more likely to be accepted and maintained rather than abandoned after initial excitement fades. By the end of this topic, you should see hyperparameter tuning as a controlled exploration where the goal is to find robust settings efficiently, not to squeeze out the highest possible number through endless trial and error. Grid search is systematic and useful when the number of important hyperparameters is small and the candidate ranges are well chosen, but it can waste effort as the space grows. Random search often finds strong settings faster by covering the space more broadly and by naturally exploring orders of magnitude, especially when only a few knobs truly matter. Guardrails keep tuning honest by preventing leakage, limiting repeated overfitting to validation data, enforcing realistic constraints, and prioritizing stability across folds, time windows, and segments. When you combine these ideas with disciplined evaluation, you end up with a model that is not only better on paper, but more likely to behave consistently when it faces new data. That is what efficient tuning really means: fewer experiments, stronger evidence, and a clear path from a tuning result to a trustworthy deployed behavior.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.